In this video, we're going to learn section 3, joint distribution. If you have the textbook, you may notice that in my slides, I'm actually doing a little bit more than the textbook. That means the content, let's say in this section, it's not that crazily important for the SOA exam. But I do believe, section 3 or some other abstract content is important to the understanding of this course, at least from more higher level of understanding. That's why I still want to do this section, joint distribution. Joint distribution, let's begin with two random variables. So it's like a two-dimensional joint distribution. You can quickly generalize to any finite dimension. Given two random variables, x and y, the joint CDF of them is defined by the probability that actually is the intersection, right? So it's the joint, it's the probability that x less than x, y less than y. So if you draw the graph, it will be two-dimensional. So if you draw the area, so let's say this is x, this is y, right? So for any given level, so x, I'm looking at the left-hand side. So for any y, I'm looking at the portion below the horizontal line, right? So, but of course, if we consider non-negative, it will be within the bounded by the two x-axis, right? So a quick observation is that if you take y to be infinity, if you take y, small y to be infinity, then the second part does not mean anything, right? Because in the end, this is intersection. So if you have this, obviously the second part always holds true, which means it is the full sample space, right? And if you have a set intersect the sample space, it is nothing but the set itself, right? And then, it's simply you are talking about the probability that the random variable x is less than small x. That is exactly the definition of the CDF of x, right? And similarly, if you take small x to be infinity, you get the CDF of y. So that's sometimes, we call the marginal, the CDF from the joint CDF. If x and y are discrete random variables, you can define this, okay? This only works for discrete. Keep in mind that not all of them will have a positive value. It's likely that, they do not happen at the same time for many small x and small y's, okay? If you want to study some the probability over a certain area, you need to do the integration, okay, with respect to the corresponding intervals. So that is a quick definition of joint distribution. Once we have joint for two random variables, it's quite straightforward, right, to define it for n random variables, okay? So the definition it's rather straightforward, okay? And a quick result is you can plug in any thing to be negative, infinity, then you'll get 0. Because what we are doing is intersection, right? So let's say we have A1 intersect empty set, intersect A2 or anything, in the end is empty set, right? And we know empty set is probability 0, right? And when do you get empty set? Is when you have one of the random variables less than or equal to negative infinity, right? That will never happen, so it's an empty set. Once one of them is an empty set, the whole intersection is going to be an empty set. So that will be 0. And also we know this less than positive infinity is the sample space, right? So in order to get everything to be, in order to get the intersection to be the full sample space, you must have each and every one of them to be the sample space, right? So that is the only scenario, you still get the sample space, right? So that's why you need to take everything to be positive infinity if you want to get one, if you want to be guaranteed to get one, okay? So here I have a quick question for you. Here I want to know the probability that x1 is between a1 and b1, x2 is between a2 and b2. I ask you to draw a graph in two-dimensional space. So here is x1, here is x2. Assuming here is a1, here is b1. So I have this, I have this. Okay, so let me get a different color to draw the horizontal line. So assume here is a2, here is b2. Okay, so obviously what we are trying to calculate is in between, right? Again, it's the intersection. So that's the intersection we are looking for. So how can we calculate the probability of this portion, right? So think about that, right? It's not entirely trivial, right? You need to work on a few things, right? So for instance, you should start from this point, right? This point includes everything, downwards, right? Including the portion we are trying to calculate, actually more than that, right? It also includes this part. So you need to do a proper subtraction of this, right? So think about that to see whether you can get the result. So given two random variables with a joint distribution, we can quickly calculate the function of those two random variables. Okay, here we want to know the expectation. So of course, when you apply a function, you get to a real value. So it's from R2 to R. Okay, so it's from two-dimensional to one-dimensional. So G of X and Y will be a real number. Okay, of course we know how to calculate, right? So the reason why I introduce so many things is because we will study something, a specific case of G. For instance, we want X plus Y. Okay, so that's one of the easiest case. Sometimes we may consider the linear combination of many x's. So here we have n x's, and each with a weight ai. So we may want to consider those. And sometimes we may consider the product x times y, right? So that is the reason why I introduced joint distribution, because that is, to me, is the right way of starting everything. Of course, in many applications, they just start with x plus y. Technically speaking, it goes from the modeling of joint distribution first, and then you apply a function g to the joint distribution to get the new random variable. But in most actuarial science textbooks, people simply write x plus y, x times y. That's not wrong, but not entirely rigorous. Let's put it that way. Okay, so here it's slightly more formal to define the operations of random variables. Okay. Covariance, we introduced this from the exercise part. Here we have well, let's call it the lead definition, right? So we already know what is the covariance of two random variables. Here you can think you start with the joint distribution, right? And your G is x minus the mean of x times y minus the mean of y, right? So I construct a new random variable out from the joint distribution of x and y. Okay, and now it is a new random variable mapping from x and y to a real number. And of course, this, well, let's call it z. Right, so z is a random variable. Of course, I can take expectation for it, right? So the expectation of z we call the covariance of x and y. Okay, Again, that is the entire reason why I introduced the joint distribution, why I start with something slightly more abstract than needed in this course. Once x and y are the same, that's the variance, and positive covariance means they are positively correlated. In the graph, that would be when x increases, y is more likely to increase as well. Okay, so they move along the same direction. Of course, when you have negative correlation, they move along the opposite direction. With this, we can, and often it's helpful to define the correlation coefficient. Okay, sometimes to emphasize it is the correlation coefficient between x and y, I will use subscript x comma y to denote it's the correlation between x and y. So it's covariance divided by the corresponding standard deviation. Obviously, we know low is between 0 and 1, and I actually ask you to prove y, not the other one, -1, 1. Y low is bounded by 1, right? So you can quickly prove that. So the next important concept is independence. Okay, that is quite important concept in elementary probability. There are different variants of definitions. Here, let's look at our definition. Two random variables x and y are said to be independent if the joint distribution equals the product of the marginal distributions. Okay, that is our definition. Quite often, if you consider continuous random variables, it's often defined in terms of PDF, right? So small f is the PDF. So if two continuous random variables are independent, then the joint PDF is the product of the individual PDFs. So that may be the definition you see from your first probability course. This obviously it's more general. Okay. Often from the definition, a quick, let's say, corollary is that if two random variables are independent, then you have this. This is really nice. So if x and y are independent, and you apply two functions to x and y, okay, so it can be the same function. So gn and h can be the same function. So if x and y are independent, after applying certain transformations, they remain independent. That is a really, really nice property, okay? And because they are independent, the expectation of the product is the product of expectations. So that is a nice thing of independent random variables, okay? You can quickly check, right? Why this is true, right? This is quite obvious, right? So if you have continuous random variables, what is cx1? So that is, let's assume they go from -infinity to infinity to infinity. So here's xy times fy dxy, right? And because they are independent, so I can separate them into x times fs dx times, because I can separate them, right? Or in other words, you can do one first and times the other, right? And when you integrate with respect to x, you treat y as constant, right? And there is no y in the integrand part, so I can factor them out. So indeed, they are. If they are independent, I can separate the expectations, right? So of course, if here is not x instead of gx hy, of course I can break them as well, right? So it's very easy to see, and we can do the full generalizations, right? Well, you can generalize to n random variables, and the same property still holds. So that's nice. So basically, the summarization is that for two random variables, for two random variables, if they are independent, they will remain independent. Okay, and given that they are independent, the expectation of the product is the product of the expectation. That is the property we often use. We actually use this a lot. Okay, one common confusion is that sometimes people equate uncorrelated to independent. Okay, and that is not true. Okay, correlation is about linear relation. Independent is about the general relation. So if x and y are independent, they must be uncorrelated. Meaning, independent. It's somehow using layman's words. They have no connection. So there's x has nothing to do with y in any sense. In particular, in the linear sense, right? So when x and y are independent, they have no connection. So it means they have no linear connection. No linear connection, which means the correlation is zero. Okay. However, correlation being zero does not mean they are independent. Right? Correlation being zero simply means there is no linear connection. No linear connection does not guarantee there is no connection. Right? There can be non-linear connection. Right? So that's why independence is more general. Okay, it includes linear connection as a special case. It also includes non-linear relations. Okay, and but the correlation only talks about the linear relation. Uncorrelated only means they do not have any relation in the linear sense. Okay, so that's why here, if they are uncorrelated, the only thing you know is this. Okay, here we have example 6. I'm not sure whether you can work that out, but you can try. Okay, at least. So here we have a uniform random variable. You define x to be the cosine and define y to be the negative sine. It's not terribly difficult to show the expectation of x is 0. So for instance, let me do that. From 0 to 2 pi, x is cosine theta. So it's, let's say, cosine theta times the density of theta, which means is 1 over 2 pi d theta, okay? And the antiderivative of cosine is obviously sine function. So it's sine theta from 0 to 2 pi. Sine 0 is 0, sine 2 pi is 0, so it is 0, right? But you can also get e of y 0, and then later on we do cosine theta, sine theta. All you need to do is this formula, sine. So the double angle formula, right? So you can also get the antiderivative. It's cosine 2 theta, and both cosine and sine, they are periodical function, right? So 2 pi is the period, so it's always 0. So you can say 0. So they do not have linear correlation, but obviously they have a relation. X squared plus y squared is always 1. So they do have non-linear relation, right? So their relation is a circle, right? So x squared plus y squared is a unit circle. They do have a relation. In fact, if you know x, you know y. Y must be one of the two values, right? So if you know x, y will be plus minus 1 minus x squared, right? So you actually know the value of y. It must be one of them. So they are not independent, but they are uncorrelated. Okay, let's continue. Example 7. How about I leave this to you? Okay, it's the first part. It's slightly complicated. It's now let me leave this to you because it's not entirely easy. So I will leave this to you as some extra work. Okay. If you can't solve this, and if you are interested in knowing the solution, maybe we can work this out during the office hours. So this is really the important part. Okay, we introduce everything to get to one point, to introduce the independence. Once we have independence, we have this nice property that the expectation of the product is the product of expectation, right? So And we do one application. So now we have n independent random variables. So all those x1, x2 are independent, okay? And I want to study the sum of them. I want to know the summation. X is the summation of all xi's. How about the MGF of x? So it's ETX. So by the definition of x, this is tx1 plus tx2 all the way to txn. And obviously, by the property of exponential function, this is product from 1 to n e of txi. And because they are independent, xi's are independent. Once I apply exponential function, they remain independent, right? So these are independent. So if I introduce yi equals e of txi, so all those yi's are independent. So I can move this outside, right? Because they are independent. And for each term, they are nothing but the MGF of xi. So the MGF of the summation is actually the product of all MGFs of the components, right? That is very, very helpful. And in most cases, we further assume all those xi's have the same distribution, meaning they have the same MGF. So all we need to do is raise the power to n. So that really, really helps. Okay, so that's the part I want to introduce. So basically, for section 3, the most important results are included in the final slide. So I will stop here and see you in the next video.